For obvious reasons, I have to say how grateful I am for the Abel Foundation for giving me this opportunity to speak on Langlands' work. And that in itself is a great pleasure and a great honor for me to just discuss, say something about the work of Langlands. Now, it's possible that there was a slight miscommunication as to what the audience would be. At first I heard that the audience for this lecture should really be non-mathematicians, people perhaps who have an interest in mathematics. But then it was also said later, after I prepared the lecture, that it should be for people, mathematicians who are in other areas. I geared it, I tried to make the lecture more appropriate for the first class of people. So I will apologize to mathematicians here if I am a little too elementary, or if I speak, if you're giving a general lecture in mathematics, you have a lot of imprecise statements and a lot of analogies and metaphors, and there will be some of that for which if mathematicians may, I apologize if that's not quite appropriate for some of the mathematicians. But so, in some sense, the Abel Prize citation was, among other things, the award to Langlands is for a grand unified theory of mathematics. Well, that's a pretty strong statement, and this, in fact, in my title is a strong statement. I don't mean literally that it unifies all of arithmetic geometry analysis, but rather that some of the most profound and fundamental ideas from these three subjects are in fact unified by the program of Langlands. I just point out a program is not something that's done, it's a blueprint and strategy for the future. And while there's been a great deal of progress on the Langlands program since it was introduced in 1967, much of it by Langlands himself, there is still a great amount to do. It's beautiful, beautiful stuff, and we can all look forward to progress in it as the years unfold. So let me first qualify those three very general areas to something slightly more specific. By arithmetic, I mean number theory, or what in mathematics is called the theory of numbers. By geometry, I mean algebraic geometry, whereby the shapes and spaces that you define are by algebraic polynomial equations, and I'm limiting those, in fact, to ones with rational numbers as their coefficients. And analysis, by that I mean a branch of analysis called, generally referred to as harmonic analysis. Let me go back just very briefly. I'm going to confine, rather than give a list of the many fundamental results of Langlands, it will be enough if I can, perhaps more than enough, if I can try to describe what it means in general terms for a unification of these three broad areas of mathematics. So much of what I say will be simply trying to put in perspective what these three areas are, and specifically what the conjectures of Langlands postulated about them. But before I do that, I can't begin without the earliest really fundamental work of Langlands that came before the Langlands program was proposed, and it's known as the theory of Eisenstein series. So it's a complete, well, in terms, specific mathematical terms, it's a complete description of the continuous spectrum of general spaces of automorphic forms. And in doing this, not too many years after his PhD, Langlands simultaneously generalized and extended the work of two giants of the period, Harishchandra I think in particular it's been alluded in this conference to how much Langlands took from the work of Harish Chandra. He was a titan of mathematics in the 50s and 60s, and the techniques which he introduced for what is known as the representation theory or harmonic analysis of Lie groups, semi-simple Lie groups, were the techniques. Langlands was the first person, I think, in the world to really understand these techniques. They seemed impenetrable to everybody else. Langlands felt they were not impenetrable and understood them. And at the same time, a figure that's very well known in Norway, a very strong figure in his own right, Otto Selberg. And in both of these cases, their work, some of their fundamental work, was extended and placed in a broader context by this one 260-page manuscript of Langlands. Okay, so that was, I guess, the background for this famous letter that Langlands wrote to André Weil. And you've seen this probably several times in the last 2 or 3 days. Langlands went to André Weil and wrote a 17-page, handwritten, highly compressed letter from Langlands to André Weil in January 1967. André Weil was the leading number theorist of his time. He also had a ferocious reputation. I don't know if it's entirely deserved. It probably is. And Langlands prefaced his letter with what you've seen here. In response, well, he wrote the letter and he said, if you are willing to read this paper, this letter as pure speculation, I would appreciate that. If not, I'm sure you have a wastebasket handy. So these pictures actually may not be entirely accurate. I think this is 2 or 3 years earlier for Langlands. He would have been 30 when he gave this letter to André Weil. This might even be pardon me? Later. The letter's later? So like 1960 or something like that? It was taken in 1967, I think, in 30. Oh, okay, so it's about the right time. It's about the current letter then, yes, and contemporary. And I don't know this picture of Weil. I don't know if that's quite contemporary or not, but you get the idea. This young associate professor at Princeton approaches the man who is the leading number theorist of his time with a series of really well-founded but very dense proposals that would turn the last 150 years of number theory on its head. So it was, at the very least, it was a bold gesture of Langlands, and that is generally regarded as the beginning of the Langlands program. Now, let me just take an aside. A rough analogy with physics. My understanding is that fundamental physicists call what they are looking for as symmetries, by which, to me, it doesn't seem quite the same as what we mathematicians think of symmetries, where different figures are the same if you rotate or translate them. But for physicists, my understanding is symmetries are unification of laws of nature, whereby laws of nature are compressed. More complicated laws are compressed into more compact laws. And of course, the most famous example probably is Einstein's equivalence principle, whereby gravity was assumed, that was taken basically as an axiom, to be indistinguishable experimentally from the force due to acceleration. But if one thinks about this, and in particular if you're Einstein, you are forced to the conclusion that gravity causes light to bend, and from that space is curved. depending on the distribution of mass, which of course has absolutely profound implications for the physical world. But I see, personally, the Langlands program as not dissimilar to this. It's a profound theory of symmetry, perhaps in this sense, in mathematics, which represents a unification of fundamental laws of arithmetic, geometry, and analysis. All right, so that's sort of the setting for my attempt to describe what these laws are and what the three areas in question are, and what are the aspects of these three areas in question. So, okay, on the three basic areas, the first would be number theory. So, okay, I apologize if you're a mathematician for this very somewhat childish description of what number theory is. It's very old. It's the fundamental properties of numbers, especially prime numbers. 2, 3, 5, 7, 11, and so on. 1 is not a prime number for reasons that might not be immediately clear if you're not used to these things, but which is a convention that we adopt. There's infinitely many prime numbers, something that was proved by Euclid 2,000 and plus years ago. Every integer factors uniquely into prime numbers. That's known as the fundamental theorem of arithmetic. And so example 133 has this decomposition in terms of prime numbers. Another example, this is kind of peripheral to what I'm talking about, but there's a much larger number, which happens to be a product of just two prime numbers, each of which is in turn very large. This particular phenomenon, or this particular property of large numbers, namely large numbers that factor into a product of only two very large prime numbers, turns out to be very important for encryption and coding. And there's a book called A Friendly Introduction to Number Theory, that's good, by Joseph Silverman, which explains how this property of numbers can be used to encrypt messages, and he explains how to use that particular factorization to encrypt the phrase to be or not to be. To set I'll give one more example. This is much more to the point of what we're interested in about factorization into prime numbers. Very many years ago, a young, how should I say, a young, brash and unsophisticated student went to Professor Langlands and asked him, "What good is number theory?" And he was very polite, and he was very encouraging, and he said, "Sit down." And then he said, look at that n squared plus 1, where n ranges over all integers. And look what factors occur in that number, those sets of numbers, as you factor them into primes. There's going to be 2. You can see what you do for the first few numbers, as he explained many years ago. 2 occurs. That's exceptional. But then the other ones, 5, 13, 17, and so on, that's not all prime numbers. It's the kind of half of the remaining prime numbers, the odd prime numbers. Namely, the ones such that if you subtract 1 from them, it's divisible by 4. So that's kind of half of the prime numbers. You don't get 3, you don't get 7, you don't get 11, and it's easy to prove that that's, in fact, a general phenomenon for that equation. And it was explained to, as you can imagine, that student was me, and it was explained to him that this is a part of, excuse me, very famous law, a very famous theorem of Carl Friedrich Gauss, his so-called law of quadratic reciprocity. Very old. So it's a very old problem to find similar laws for the decomposition of other sets of prime numbers, not n squared plus 1, but where you take some other polynomial. Now, actually, if you take a quadratic polynomial, something like this is always going to be happening. But if you take a cubic polynomial, you could, if you're just beginning in mathematics, you can take it home and experiment with it, and it's not so simple. If you tried it with a fifth degree polynomial, there would appear to be no pattern whatsoever. But in any case, this is a fundamental problem. It's more than just a curiosity. It's a nice phenomenon, but it's more than just a curiosity. It's not hard. It's known that a suitable answer to this question for general polynomials, can you characterize their factorization into primes, that's very closely related to what would amount to a classification of number fields, that is to say, fields which are finite extensions of the rational numbers. So that's the third example in number theory, and it's that example that is the solution to this old but very important problem. The solution to that problem, excuse me, that is one of the things that the Langlands program answers. Langlands also said this Gauss would have been thrilled to have a theorem that had such laws for cubic or fourth degree equations. He really would have liked that. But it is now part of the Langlands program, although I have to say it's not part of the Langlands program that has yet been proved. Parts of it, little bits of it have been proved, but not in general. Okay, so that's all I'm going to say, setting the background for number theory. The second area, algebraic geometry, is really it's really a generalization of the first. So algebraic geometry is the geometry of objects that you get by solving polynomial equations in several variables. So the first one, example, x squared minus 2, that has two solutions. That's just, well, it's like the earlier problem in arithmetic where you have one equation in one unknown. You have only finitely many solutions. So that's where it's for those kind of equations that algebraic geometry specializes to the number theory question I was looking at. But it also includes, say, an equation in one equation in two variables, say x squared plus y squared equals 1. And that is, as we all know, that's if you plot that on the xy plane, that's the unit circle. Center 0, radius 1. That's of dimension 1. When I was in high school, we studied these things, and probably many of you did. You studied second degree equations in two variables, or ellipses, circles, or parabolas, or hyperbolas, and that's it. But it gets more interesting if you go even just to a cubic equation, excuse me, in two variables. Excuse me. Y squared equals x cubed minus x. When you do it in a cubic equation, it's the solutions are what are known as an elliptic curve. It's still in dimension 1, but it's a lot richer, and there's a huge amount of number theory involved with elliptic curves. And in fact, they are at the heart of Wiles' proof of what led to the proof of Fermat's last theorem. He had to prove something about elliptic curves. So already those are very interesting beyond just factoring polynomials in one variable. And in general, algebraic geometry, you would have, say, many equations, say m equations, in many variables, say n, with n bigger than m. And then you'd have something that would be of dimension n minus m. So as you could well imagine, such things are going to be very complex, and they contain, as well as geometric information, they contain all kinds of extremely interesting arithmetic information. Okay, so now it's in this setting that perhaps one of the really, truly greatest mathematicians of the 20th century proposed a stunning conjecture about such algebraic varieties. Alexander Grothendieck, he proposed a theory of what became known as motives. And I guess, I mean, to me, these are the ultimate, certainly from the point of view of this discussion, these are the ultimate objects in algebraic geometry. By a very abstract series of deductions, he postulated the existence of what he ended up calling, he called them motifs. He actually asked, the story that I heard, I don't know if it's apocryphal, when he discovered these things, he asked some of his friends in art and literature, what do you call it when you have, say, a piece of music where a theme that is played that somehow represents the ideas in the music, but is beyond the ideas of the music? Or in a painting, you have an idea that is not concrete or explicit, but somehow represents the ideas of the painting. And he said, oh, he was told, it's a motif. That's what we call a motif. So he said, yes, okay, so the story goes, that's what I will call these objects in mathematics. He, that somehow got translated into English, not as motifs, but as motives. So motives, I can't say what they are, but it's very complex, but a very beautiful theory of their existence, which, depending on how you define them, is still not, even that is still not completely formulated. But what they represent are hidden building blocks of algebraic varieties, somehow sub-objects of algebraic varieties that when put together yield an algebraic variety. Hidden building blocks of algebraic varieties, which are deep, which are abstract, and then from our purposes, which come with internal data, just the way they're set up, they come with internal data associated with prime numbers p. And in the trade, these numbers, these data attached to numbers p in the trade are known as eigenvalues of Frobenius operators. And I think it's fair to say that the ideas of motives are not at all unlike the way physicists think of matter. If algebraic varieties, as we've agreed, are the solutions of algebraic equations, if they're to be thought of as the objects of everyday life, I don't know whether that table looks like an algebraic variety. It probably does to some approximation. Then the motives would, by this analogy, represent the fundamental particles that go into this object. So motives, I think it's a good analogy to think of them as kind of the analogs of fundamental particles in physics. So that's the ultimate object from this discussion, from algebraic geometry. And so then the third area is what I've called harmonic analysis. So harmonic analysis these days has actually quite a broad interpretation. And what is harmonic analysis? Originally it was the analysis of harmony. It was literally the analysis of harmony. But that's most usefully illustrated, most simply illustrated by what happens if you have an elastic string which is fixed at two endpoints, and you take the string and you lift it up and you pluck it and let it go. And you will hear a note. You will hear a note of a certain frequency. But you actually, your ears don't distinguish it, but you are actually hearing more. You are hearing the sound of a given frequency, which is determined by the length of the interval and the tension of the string. Whoops, don't want to give anything away here. you are, that frequency that you hear is just what would be called the first harmonic, but then there are other harmonics as well. Notes, this one would be a note whose frequency is 3 times the frequency of the original one. This is 5 times the frequency of the original one, and only those ones occur. But they occur as you go on through all odd numbers. And I guess those are known as the supplementary harmonics, or maybe sometimes called overtones. And it's those extra notes which make the sound of a plucked string give its particular sound. In the sense that if you pluck the string differently, suppose you put 2 fingers on it and you went to the left and you lifted one up, and on the right you put one down and you let both of those go, you would have a different sequence of harmonics to go with the basic harmonic, to go with this one. It depends on how you pluck the string in the first case, and the note would sound different. It would have a different sound from the original one. And I think if you, and I never really read on this, supposing you, a very great cellist played the bass note of a Stradivarius cello, that would have a different sound altogether, and I don't know what it would give it its particular beauty, but much of it is in terms of the string and the way it is bowed. So the analysis of the sound that you hear from a plucked string, that's as many of you know, is a theory of mathematics known as Fourier series, and it describes how the different, depending on how you start the string off, it describes the various overtones or harmonics. A more sophisticated example is sometimes called hearing the shape of a drum. And by that I mean a planar drum surface with a boundary, which is quite irregular. This bottom part is not so serious. That just amplifies the sound. What kind of sound you hear is based only on the shape of the planar surface. The geometric shape of the top of the drum determines what we could call the spectrum of frequencies of its sound, different frequencies which depend on the geometric shape of the drum. Or in other words, the shape of the flat drum head is the same thing as, well, in mathematics, the mathematical term for that is the eigenvalues of the Laplace operator on this region, the surface of the planar surface of the drum. So, I mean, there are some sort of pathological examples, but basically the shape of the drum determines exactly the sound that the drum makes when it is hit. And we're not in the habit of constructing drums with peculiarly shaped boundaries, but if you did, it's an interesting question as to what the sound makes. And actually this is a general phenomenon whereby geometric objects, in this case the shape of the drum, give rise to spectral objects. And by spectrum I just mean the continuum of frequencies that make up the sound of the drum when it is hit. This is a phenomenon that goes all throughout mathematics. Geometric, I don't mean geometry in the sense of algebraic geometry, but just ordinary geometric objects in many cases determine spectral objects, and conversely. And that's the context in which harmonic analysis is understood these days. Well, if motives were the ultimate objects in algebraic geometry, then the ultimate objects in our discussion for harmonic analysis are known as automorphic forms. And we've heard automorphic forms mentioned regularly in the last 2 or 3 days, and I have to try to say what they are. They are well, they're really quite profound. There's profound spectral objects, and I'm just going to say the words of the mathematical setting for them. They are profound spectral objects, namely eigenfunctions of Laplace operators, on certain spaces, x of g, which are known as locally symmetric spaces, attached to other mathematical objects, reductive algebraic groups, known as reductive algebraic groups G. But the point is that by analysis, they come with frequencies, which are really the same thing as eigenvalues of Laplace operators. They also come actually with supplementary numbers, p-adic frequencies. So we have these numbers coming from which are the basic frequencies or eigenvalues of the Laplace operator. But there are supplementary ones which are parameterized by primes p, and these are known as eigenvalues of Hecke operators. Professor Langlands spoke of Hecke operators in the slightly different context of geometric. I don't know if I call it geometric Langlands, but the geometric program, and where they're related, but different. This is what I'm talking about is what was referred to this morning as the arithmetic Langlands program, the original one. But in any case, automorphic forms are objects which come with frequencies. I'm using the term frequencies here. This is not a term that's used by mathematicians. They use the terminology eigenvalues of this Laplace operator or eigenvalues of Hecke operators. And you could ask what sound this would make. Do these objects make any sound? And they don't. They're higher dimensional. I mean, you can leave it as a philosophical question that if you built a higher dimensional machine, whether it would create sounds that were particularly interesting. But in any case, they are exactly the same formal objects that come from the frequencies that you get from hitting a drum, but they're much more sophisticated. So this is pretty suggestive. Any automorphic form, with being an object with this kind of data attached to it, it comes with a rich set of spectral data. So this is pretty suggestive because motives, which I was calling the ultimate objects in algebraic geometry, also come with a set of numbers attached to prime numbers. And they come from a totally different area of mathematics. They come from solutions of algebraic equations in many variables. These things come from something that is like a generalization of Fourier analysis, totally different. But beyond being suggestive, there's something really critical that happens with automorphic forms that does not happen with motives. And that is, at least does not initially happen with motives, that is, the objects G, the objects that give rise to automorphic forms, can be classified. There's a complete list of all groups G whose spaces give rise to automorphic forms, and hence these families of data. So let me show you a picture of the basic groups G that we're talking about. It's the classification that was done in the earlier part of the 20th century of all of the different, these are actually what you could call the basic G, specifically the simply connected split groups G. But every G can be gotten from one of these objects, by a well-defined and uniquely determined process. And these ones, well, I mean, one doesn't have to know what the diagrams actually mean, but they are rather intriguing if you don't know what they are. There's one G for every one of these 9 diagrams, and for every n, where there's more than one n. So for every one of these diagrams, there's a unique G. These diagrams all mean something about what the group G is how it's put together. So this actually is I think what makes the whole thing work. I haven't said what the fundamental tenets of the Langlands program are, but this fact that you can classify these G is what makes it all work. All right, so now I can describe, with this background of these 3 different areas, I can describe the 2 fundamental tenets of the Langlands program, or let's call the 2 pillars of the Langlands program. One is known as the principle of functoriality. So it's an outgrowth of the letter Tve. The ideas in it were basically set down in this handwritten letter of Ve, but were later elaborated by Langlands a couple of years later in a longer article, which he published. So the principle of functoriality, it's known as a principle, but it's really a conjecture. It's a beautiful but very deep conjecture that characterizes the relations among different automorphic forms and the data that they contain attached to different G. I don't know how that sounds, but if you can classify these objects G, and if each G comes with a family of automorphic forms that has this data attached to it that looks like prime numbers and numbers coming from eigenvalues of Laplace operators, then you might ask, are some of them related to others? And the answer is yes, they are. And the principle of functoriality is, I'm not going to say exactly what it is, but it tells you exactly when 2 automorphic forms attached to 2 different groups G, when they are related to one another, or whether the data from one it can be expressed simply in terms of the data of the other. So in other words, if these automorphic forms and the different groups are supposed to classify something, then they themselves are completely determined, in a sense, if you know all possible relations among them. And that's what the essence of the principle of functoriality says, the relations among these things. It was completely unexpected. And I said 150 years of number theory. Well, it's now 2018, and it was not really, the principle of functoriality was not really, I think, understood or accepted by people, even number theorists, for many, many years. So I'm now talking about 2018, so I will allow myself to say it changes the course of 200 years of number theory. The second tenet is what we've been sort of heading towards, hinting at, and it's known as the reciprocity conjecture. This is more recent. This was proposed in 1977 by Langlands in the proceedings of a conference that was held at Corvallis. And what it is a classification of motives, not just automorphic forms, but motives, these fundamental building blocks of algebraic varieties, and the data that they contain, that is to say the specific numbers, in terms of automorphic forms, these things that we have agreed are classifiable, and the spectral data that they contain. So for every motive, there's an automorphic form, and such that the data attached to the 2 objects is matches. That's what this conjecture says. There was an earlier special case of this conjecture. This was proposed in 1977 by Langlands. An earlier case of it was proposed about 1955 and is known as the Shimura-Tanyama-Vei conjecture, which applies only to the motive attached to an elliptic curve. Very, very special case, where M is the motive of an elliptic curve, and elliptic curve actually has three motives attached to it, two of which look like the motives attached to a circle or a hyperbola, but the main one, the new one, is what I'm talking about here. It's the motive attached to an elliptic, whereby the motive of an elliptic curve, M is the motive of an elliptic curve, some elliptic curve, and G actually is equal to the simplest of these groups, the one that would be A1 in our picture. So in other words, just this one up here, AN, N can stand for any number of vertices, and I'm just talking about A1, the group that is attached to just one vertex. So it still was very, very deep and interesting, but it was, in this general scheme of things, it was perhaps the simplest possible group. In any case, this Shimura-Tanyama-Vey conjecture was proved by Andrew Wiles, and I think perhaps colleagues for some of the remaining cases, in order to, it was known that if you could do that, you would be able to establish Fermat's last theorem. And I would just like to add that if we are to understand that motives are like fundamental particles in physics that compose our objects of everyday life, and specifically algebraic varieties, then this reciprocity conjecture might be regarded as a classification of the fundamental particles that gives their physical properties: mass, charge, spin, etc. Now, I'm not saying that I am not saying that this is the same thing as physics. It's not the same at all. It's purely an analogy. But to me, it seems quite striking and beautiful. I am told that when Langlands published his paper on functoriality in 1970, which was basically, it wasn't even called functoriality in those days, but the elaboration of his letter to Vey, that a very distinguished algebraic geometer read it and said, "This is all well and good, but how would you ever prove anything like this? There's no way you could get your hands on these things." But actually, Langlands had ideas in mind for that as well, which he did not, he spoke of them, but he didn't write them down explicitly. And they have to do with the trace formula. But the trace formula, I think, in Langlands' mind was perhaps to serve as the muscle that would eventually be able to prove some of these conjectures. So I'm going to, I would like to talk about some of Langlands' results now, but I can't make any systematic description of all of the results. So what I'm going to do is confine myself to the results that he did that have to do with the trace formula. Excuse me. So that's what I've written up here. The trace formula in the time 1970, it was a very striking formula that Selberg proved and wrote out for certain of the G in my diagram. Langlands envisaged a general case trace formula that would apply to any G. And his theory of Eisenstein series, which you'll recall I mentioned right at the beginning of the article, would be a key ingredient of it. It would be a complex identity relating hidden spectral data in automorphic forms on any G. That's what we want, but with more concrete geometric data in G, and that perhaps is what you might hope to compute with. So in analogy, it's like the shape of the drum being the geometric side of the trace formula doesn't really apply to the sound of a drum, but if it did, it would be the shape of the drum that's somehow incorporated on one side of the formula, and the frequencies that would be on the other side. Okay, here's a picture. For what it's worth, here's a picture of the trace formula. It's that formula at the top, and it's got many undefined terms in it. But just one thing one can note is that the two sides of the formula have a symmetry. They look very much like each other. So the general structure of the two sides is rather similar. But in any case, the left-hand side is what contains geometric sorts of data, like the shape of the drum, the shape of the boundary of the drum, more concrete things. And the right-hand side is the spectral data that's hidden and that you want to know about. Concrete geometric data in G, hidden spectral data in G. And F, there's an undefined object there. It's a function. It's known as a test function, and it's something that you get to choose. And for every F, you get a formula like this, which gives combinations of geometric data, depending on F, equal to corresponding combinations of spectral data attached to the given F. So F's a test function. We get to choose it. And I think you could make an analogy with physics by saying that choosing F is like designing an experiment to find concrete physical data, namely in this context the left-hand side of the trace formula, with which we could then try to compute the hidden spectral data, which is there on the right-hand side. Early use of the trace formula, which is what Selberg did, and many people that was before Langlands entered the subject followed up, was to use the two sides of Selberg's formula to get estimates of what you couldn't write down. So in other words, to apply it to a group G in isolation. Estimate the geometric data, maybe such things like lengths of geodesics on a Riemann surface, etc., or spectral data, eigenvalues of Laplace operator, to estimate one of these two kinds of quantities by somehow getting some more precise information about the other side of the trace formula. So it was they used the identity for a given group G to try to make estimates of these kinds of very sophisticated data on either side of the trace formula. Langlands' emphasis, I think it was perhaps used by a student of Shimura in some very special case, but Langlands was, I think, essentially the first person to propose a completely different use of the trace formula, whereby you didn't try to calculate the things on either side, but rather you would compare trace formulas for two different groups, G and G prime, by to establish what you would want to do would be to establish deep relations among the spectral data for two different groups, G and G prime, by proving exact, not approximate, not an estimate, which is what had been happening before when you did the trace formula for one group, but when using the trace formula for two groups, proving exact identities between their corresponding geometric data. So the spectral data, that's the stuff that has to do with prime numbers, the stuff you really want, it's hidden. And the principle of functoriality, that's what the principle of functoriality as a conjecture applies to, this hidden data, relations among these data for two different groups. And Langlands, he, I think, had to really be quite aggressive, and it didn't really help for a long time to get people to think of using the trace formula in this way, rather than using it in the original sense, which was interesting in its own right, but it was very different from what this was capable of. And this is what Langlands emphasized, and it led to proofs of this principle of functoriality in various cases. And in fact, insofar as the principle of functoriality, which is, I think, really the deepest of it's the essence of the Langlands program, or, well, they're both of the two pillars are very important. But I think it's fair to say that more or less the only cases of proofs of functoriality, with one or two exceptions, have been by this strategy. So this led to proofs of functoriality in various cases. So I'm just, as I say, I'm giving short shrift to the many things that Langlands did that are not related to the trace formula, but related to the Langlands program in other ways, having to do with fine points of the geometric data and the spectral data. But Langlands' work having to do with comparison of trace formulas, let me just cite sort of the selection of examples. The first thing that I guess that Langlands did in this comparison was with Jacquet in 1970. It was the simplest comparison of trace formulas and corresponding special cases of functoriality applied to the group GL2. That's the group that Langlands was speaking of this morning. And if I could just go back to my diagram, it's the simplest group in this classification. It's, again, the group up here with A1. A1, the group that corresponds to just one vertex in the top row. In these cases, I've had n greater than or equal to 2, because if I put n equal to 1 in this case, I'd get the same thing as here. But in any case, the simplest possible group. But yet, there were two different groups. I've told you that the groups in my classification diagram are not all groups, but can all be obtained by a simple procedure from those groups. And that's what it's for the group. That's what one group attached to the group with one vertex, and the actual group attached to one vertex, namely GL2 on the one hand and a multiplicative group of a quaternion algebra on the other. That was the first case of a proof of functoriality by a comparison of trace formulas. The second, the first one is still being used today. This was done in 1970. It's still being used today by people to extract number theoretic consequences. I guess it's pretty well been used for all it's worth. I mean, there was a while, sort of perhaps in the 80s, people were using it all the time. Number theorists were using it all the time. The second, so it was very important, very striking. The second one, however, was really, really important. That's what I've alluded to. This is known as base change for GL2. And that's a more complex comparison of trace formulas, leading to further cases of functoriality. And in particular, it was the first progress on a very famous conjecture of Emil Artin in 50 years. Once again, it's just the group GL2, the group consisting of one vertex, but it's a slightly more complicated trace formula. On one of the trace formulas more complicated. It's known as the twisted trace formula. And the comparison that Langlands established following an idea of Shintani, Langlands realized that if you took Shintani's ideas and applied them to the full trace formula for GL2, you got something very spectacular, namely a proof of a conjecture of Artin having to do with what are known as Artin L functions, functions that are like the Riemann zeta function, but with more interesting coefficients. And the question for these particular functions, they're defined in terms of the arithmetic of a polynomial, like as I mentioned at the very beginning. They are believed to have analytic continuation and functional equation. And this is what Langlands proved as a very surprising outcome of this comparison of trace formulas. First progress didn't prove the whole conjecture of Artin, far from it. But the first progress in that in 50 years. And this was actually was a starting point for what I have mentioned before, namely Andrew Wiles' proof of the Shimura-Tanyama-Wei conjecture, and hence Fermat's last theorem. More recently, it was proposed by Langlands maybe around from 75 to 85, known as the theory of endoscopy, which I can't go into, but it's a comprehensive theory, still partly conjectural, which consists of an intricate study of the spectral data in any G in terms of group representations, leading to what's known as a stable trace formula, a more sophisticated version of the refinement of the trace formula, which would be needed for further progress. So that's still partly conjectural. To go with that, something that is known, named by Bob himself, actually, beyond endoscopy. And it's a long-term proposal to attack the general principle of functoriality, that is to say, the cases of functoriality that haven't been proved, and that's a large number of cases, difficult cases, but purely with a comparison of trace formulas. Up until now, to attack this most general principle of functoriality, nobody had an idea for using trace formulas. Langlands has proved a very ambitious and challenging strategy. It'll take many, many years for the mathematical world to make it work, but a specific strategy for using to attack the general principle of functoriality, which is the essence of the Langlands program, by a specific comparison of stable trace formulas. So that's all I have to say, and thank you very much.